You wake up, and the world has gone completely dark. A sudden failure has cascaded through the power grid, shutting down block by block until the entire skyline disappears. Your first instinct is to reach for a standard emergency flashlight, but these consumer devices usually run on an 800 milliamp hour battery. Under continuous use, that battery will drain to zero in about 4 hours. For generations, we have outsourced our basic biological need for vision to an interconnected electrical infrastructure. We flip a switch, and power flows from a plant hundreds of miles away to banish the shadows. Once the battery dies, that convenience is gone. To find light in this environment, you have to look at the physical behavior of your surroundings. When daytime arrives, finding light might seem simple, but if you are sheltering in a room where direct sunlight is blocked, the space remains dangerously dim. This illustrates the angle of incidence. When light strikes a surface, the angle at which it hits matches the angle at which it bounces off. Apply this to a room. A reflective surface opposite a window captures daylight, scattering illumination deep into the interior. This creates bounce lighting. It reduces harsh contrast and increases the perceived brightness of the room without using any electrical power. Geometry allows you to redirect the energy the sun is already providing, turning a single window into a source of ambient light for the whole room. Then the sun sets. Without ambient daylight, the absolute darkness returns, bringing immediate isolation. This microscopic view shows combustion. Heat applied to a solid fuel source like wood begins exciting the molecules within the structure. As these atoms become energized, they shed excess energy by releasing visible photons, a reaction called incandescence. A small controlled fire acts as a practical light source. The low-key shadows it casts across the room restore your depth perception and spatial awareness. A fire converts stored chemical energy back into the visible electromagnetic spectrum, pushing back the dark with a predictable reaction. Primitive fire consumes fuel quickly. For long-term survival, you need sustainable density, like a 12,000 milliamp-hour solar emergency system. A self-sufficient system relies on a closed loop. It stores solar radiation in lithium cells during the day to power LED bulbs when night falls. But a bare LED bulb scatters light rays in every direction. That wide dispersion reduces how far the light actually penetrates into the surroundings. This cross-section shows the solution, a Fresnel optical lens. The jagged, stepped physical modifiers of the lens intercept those scattered rays and bend them into a concentrated, uniform beam. Combining natural energy collection with precise optical engineering allows you to maximize the efficiency of every stored watt. When you look out over a dark city, the failed electrical grid sits in contrast to a vast, starlit sky. Inside, you have reclaimed your space. You have used angled mirrors to bounce daylight, chemical combustion to generate incandescence, and solar lenses to focus energy. The modern power grid automated illumination for us, but the physical laws of optics and energy continue to operate, regardless of whether the grid is active. When the grid fails, these principles of optics and energy transformation become your primary tools for reclaiming the night. Subscribe to the channel to keep your mind illuminated, and to see exactly how the electrical infrastructure works and why it fails, click the video on your screen now.